Welcome to video 18.3. I'm not even sure what letter to attach to it, but this one will be about back titrations with a discussion of uncertainties as well, which is definitely something that's always beneficial. Now let's start with some general theory about back titrations. And in fact, we'll really start with general theory of a regular titration first, just to help it make sense. So in a regular titration, we have a flask, we have a burette, and the flask has some known volume, and that volume is maybe something like 25 milliliters that came from a volumetric pipette, and that is typically an acid. And in the burette, you have a base, and the base has a known concentration of hydroxide. Maybe it's sodium hydroxide. That's a typical base we use for titrations. And you add the base until it changes color, and you know the initial reading of the burette, you know the final reading of the burette, and so now we know the volume, and because we know moles equals concentration times volume, I can calculate the moles of base, and because of stoichiometry I can calculate the moles of acid, and because I know because I know the volume of the acid, if I want to find the concentration, it's moles over volume. So that's kind of how a normal titration works. Back titrations are a little different, and kind of the way that a back titration works is back titrations are often done for a base, and it's much more challenging to know the exact concentration of an acid because we're mixing them from liquids, and we just can't be as precise as we can in making a base. So what happens with a back titration is I have some base. Sometimes this is a solid, like sodium hydrogen carbonate or calcium carbonate. And so that is reacted with some acid that has a known volume and a known concentration, as best as we can know that concentration. And it's an amount that is in excess. So, but if I know the volume and the concentration, I know the total moles of acid. Okay? Well, some of this acid will react. And so if we assume one-to-one, some sort of one-to-one reaction, although because of stoichiometry calculations, even if it's not one-to-one, I can figure it out. And that will leave some amount of acid that is in excess, which we will then titrate with a base. And this portion of the calculation is kind of a standard titration. So I know the moles of base that I titrated because I know the volume and I know the concentration, which means I can calculate the moles of excess acid. And if I can calculate these moles and I know the total moles, I can calculate the moles of acid that actually reacted with the base. If I know those moles of acid, I know the moles of base, and now I can learn about this base. So it's a bit longer, a bit more complicated, shall we say. So we start with some amount of base, and we know, for example, we know the mass of the base, but we don't know the number of moles. I react some amount of excess acid. Some of that acid will react with the base and be gone, no longer in the solution, but there will be some excess acid left over, which I titrate with the base using a standard titration practice. And because this total volume of acid has a known volume and a known concentration, I know the moles. And if I can figure out the moles of excess from the titration, I know I can subtract and I can figure out the moles of acid. I can use stoichiometry now to figure out the moles of base. Yes, it's a bit complicated. A little bit of practice and you'll get there. So let's try a problem. An antacid tablet listed sodium hydrogen carbonate as the main ingredient, accounting for 70% of the mass of the tablet. Sodium hydrogen carbonate. Baking soda. Sodium is 1 plus, hydrogen carbonate is 1 minus, and there's our formula. So now we get to more details of the problem. A single tablet with a mass of 0.302 grams was added to 25.00 centimeters cubed of 0.125 molar hydrochloric acid. But wait, Mr. T, we know it's 70%. What's 70% of 0.302? Well, that's what the titration is for, to see how close we are to the true value. Again, this is a quality control measure that some companies will use. So, what do I have? I have a volume and a concentration. Moles equals volume times concentration will be the total moles of HCl. So moles equals 0.02500 decimeters cubed, I divided by 1,000, times 0.125 moles per decimeter cubed. That means the moles are 0.003125 moles of HCl in total. That's the total number of moles of hydrochloric acid. So let's figure out the uncertainty of that number. The uncertainty of the concentration we have to assume is 0 because we were not given an uncertainty. But we can find an uncertainty for the volume. The uncertainty of the volume is 0.03 centimeters cubed divided by 25.00 centimeters cubed times 100 is 0.12%. So that means that the uncertainty of this value is 0.12%. The uncertainty of the mass we can figure out at a later time when we need it. So after the reaction was complete, the excess hydrochloric acid was titrated with sodium hydroxide using phenolphthalein, which is not the best indicator, and we'll learn why later. The sodium hydroxide was prepared by adding 2.05 grams of sodium hydroxide to a 500 milliliter flask. So first we need to do here is calculate the concentration of sodium hydroxide. So 2.05 grams of sodium hydroxide divided by 40.00 grams of sodium hydroxide in 1 mole of sodium hydroxide. That's the moles, and if I divide by the volume, 0.5000 decimeters cubed, I can get the concentration. So that equals 0.1025 moles per decimeter cubed of sodium hydroxide. So there's our concentration. Now, what about the uncertainty? Well, the uncertainty of the mass of the sodium hydroxide pellets is 0.01 divided by 2.05 times 100, which is 0.5%. And the uncertainty of the volume is 0.2 divided by 500.0 times 100, which is 0.54%. So those are two, sorry, my apologies. I was thinking about the total. This value is 0.04%. If you combine these values, you get an answer of 0.54% total. So that's our uncertainty. The biggest uncertainty so far has been the mass because 2.05 is a relatively small number. So I know the concentration of the sodium hydroxide that's been added, and I have the uncertainties all along the way. Now we have the burette readings, 21.1, 21.2, 21.3, 21.4. I think this is 21.33 centimeters cubed plus or minus 0.05. Over here, I think this is 25.69 centimeters cubed plus or minus 0.05, and I think that the end point is quite a dark pink, maybe was overshot by just a small amount. So I have 25.69 centimeters cubed minus 21.33 centimeters cubed. I got 4.36 centimeters cubed plus or minus 0.10. So there's our uncertainty. We can certainly turn this into a percentage. 0.10 divided by 4.36 times 100 is 2.3%. Wow, now there's our biggest percent uncertainty now. Because we had such a small volume for the titration, the uncertainty is actually significantly larger. Now, if your readings of this burette are maybe 21.32 or 21.34, that's okay. Maybe you thought this was 25.68. I don't think you could argue for 25.70 though, because you can see some space between the line for 0.70. So, but maybe 25.68. That's okay. Your numbers will be slightly different, but as long as they're reasonable, that's acceptable. Now we calculate the moles of sodium hydroxide used using our favorite formula. Moles equals concentration times volume. So I have the concentration of sodium hydroxide is 0.1025 moles per decimeter cubed, and the volume that was used was 0.00436 decimeters cubed. So I took 4.36 centimeters cubed from the previous slide, divided by 1,000. This concentration for the sodium hydroxide came from an earlier calculation. So I have 0.0004469 moles of sodium hydroxide. Now in terms of uncertainty, this uncertainty was 0.54%, this uncertainty was 2.3%, which is 2.84%. And I'm not really rounding my significant figures for my percent uncertainty here. Next, we need to use stoichiometry to find the moles of sodium hydroxide that reacted with the hydrochloric acid. So I have 0.0004469 moles of NaOH. And I know that for every 1 mole of NaOH, I have 1 mole of HCl. So that means I have 0.0004469 moles of HCl in excess. These were the moles of HCl in excess. How much of the hydrochloric acid do we have in total? Well, this should be some number bigger than this number, right? So let's figure out, let's go back and think about what we did. Well, our very first calculation was 0.003125 moles of HCl in total. I'm going to subtract 0.0004469 moles of HCl in excess. And that will give me 0.0026781 moles of HCl that reacted with the sodium hydrogen carbonate. So remember, we had some sodium hydrogen carbonate here, and we added excess hydrochloric acid. So this reacted, all of this hydrochloric acid reacted, and it's now gone, neutralized. So we had some hydrochloric acid in excess. Well, we reacted that with sodium hydroxide in a titration, and we figured out the moles of sodium hydroxide, used stoichiometry to figure out the moles of hydrochloric acid. And since I knew the total moles, and I knew the moles in excess, what we just calculated is the moles of hydrochloric acid that reacted with the sodium hydrogen carbonate. Now let's think about uncertainty. The uncertainty of the first value is 0.12%. The uncertainty of the second value is 2.84%. That's a total of 2.96% uncertainty at this point. So how many moles of sodium hydrogen carbonate are present in the tablet? And let's convert that to grams. So let's think about the balance equation. Sodium hydrogen carbonate is going to react with hydrochloric acid to make sodium chloride plus water plus CO2. It's 1 to 1. So 0.0026781 moles of HCl. For every 1 mole of HCl, there was 1 mole of sodium hydrogen carbonate reacted. And for every 1 mole of sodium hydrogen carbonate, there is a mass of 84.01 grams of sodium hydrogen carbonate, the molar mass. So I have 0.2250 grams of sodium hydrogen carbonate. And that is plus or minus 2.96%. I don't have anything new here in terms of uncertainties. This mole ratio comes from the balance equation. There are no uncertainties there. This molar mass, we're not given any uncertainties for our periodic table, and so our percent uncertainty remains the same. So now we get to calculate the percent sodium hydrogen carbonate in the tablet. So I have 0.2250 grams of sodium hydrogen carbonate in the tablet, divided by 0.302 grams of tablet. That's the total mass of the tablet, times 100. and I get 74.5%. So in terms of uncertainties, this was 2.96%, and this 0.302 is 0.001 divided by 0.302 times 100, which is 0.3%. So now I have 3.3% uncertainty overall. So I know my tablet is 74.5%, plus or minus 3.3% of the 74.5%. So let's compare this to the true value. The absolute value of the true value minus the experimental value divided by the true value, absolute value again, times 100, I get a 6.4% error. And we had a 3.3% uncertainty. And our value was too high relative to the true value. So let's comment on the presence or absence of systematic and or random errors. Well, there was a 6.4% error. We had a 3.3% uncertainty. So that means that there are some systematic errors present because the value was too high and it was above, the percent error was outside the range of the percent uncertainty. Why would that be? Well, do you remember I commented that the flask was too pink? It's likely that we overshot the endpoint, which would lead to a higher value, which would lead to a percent error. That's probably the most likely systematic error. Now, I also mentioned earlier that titrations are used as quality control for a company. So what I described here to you is more likely a student lab where you're learning about back titrations rather than somebody in lab. Somebody in a lab of a company making these drugs is going to be very precise with their titrations, very practiced, and they're not going to overshoot the endpoint. If they do overshoot the endpoint, they're going to do the titration again, and they will not be using that data, and they'll look for 2 or 3 trials in a row that have good data. And so that's something just to consider. This is much more from a student perspective. But since the percent error was bigger than the percent uncertainty, then it's likely that there are systematic errors. So that's a back titration. Thank you for listening. There are no checkpoint questions or anything like that. This is just a video for you. However, you certainly can ask questions by sending an email. I'm happy to take care of that. So let's write here questions. Actually, what I'll do is I'll use Edpuzzle. I'll make a form on Edpuzzle, and I'll give you the option to ask questions. We will take time to talk about this in class together, but if you've got specific questions, put them in the form. Thank you for listening. Have a great day.